Okay, so we've seen some trig functions within these integrals, but so now let's talk about some more complicated ones. So here's the overall strategy for this. So the first step is to simplify or change the form of the rate function. So the rate function is made up of some combination of trig functions. So we want to simplify or change the form using identities. This is going to be a big part of this. And I'm going to show you a chart of identities that I'll also post on Blackboard and we'll be using today. But so you're going to have to know these identities and recognize when they're going to help change the form of the rate function that you're given. It's also going to involve algebra, arithmetic. Okay, and then once we change the form, what's our goal in changing the form? Our goal in changing the form is either to set up for something easy, so something straightforward, like ones we've already seen, okay? Or we're setting up for undoing the chain rule. Again, here it is again, right? So that's why I said it's the first thing we did. It's what you always look for first, and then it keeps popping up in all the other techniques. Okay, so this is the deal with these more complicated ones. We're going to do some simplification first. We're going to use trig identities, maybe just some basic algebra. And our goal in that is either get something just that we can do easily, so just like a straightforward antiderivative, or we're doing this rearranging to stage for undoing the chain rule. And that's what they're all like. They're all like that. So here are the. I'll give you a second. Make sure everyone's done writing. So the scope of the trig identities that you will need. Are we good? Is these. You know what? Don't write all these down, okay? Don't write all these down, okay? But this is the scope of the most important ones that show up the most, the ones that we're going to need. So our basic definitions of tangent, cotangent, cosecant, and secant. Then we have the Pythagorean identities, all based on sine squared plus cosine squared equals 1. That should be very familiar. That will show up a lot. And then there's these other variations on that. Half angle identities are going to be really important. So, but they're actually, the half angle is kind of like turned around. So this x is half of this angle. So that's why it's called the half angle identity. But we've really changed the form to use them for our purposes. So it doesn't really look like a half angle identity, but it's in the form that's going to be most useful for us for antiderivatives. And then the double angle identities. So what is sine 2x is 2 sine x cosine x. And then for cosine 2x, there's actually 3 different variations on cosine 2x. So I will post this list on Blackboard. And as we're working problems today, we'll have it right there. So, and then when test time comes, what I usually do is kind of meet you halfway in terms of memorize them. So yeah, memorize them. But then what I'll do is I'll put this thing on the cover sheet of the test with everything blanks for all the equals, all the right sides of the equations blank. And then you can start off the test by just filling it out. So just practice memorizing this and then start off the exam by filling this out for like a bonus point on the test. And then you'll have it. Then you'll have it. You don't have to sit there and keep going back to it. So I'll give you some bonus points for memorizing it, and then you'll have that whole thing at hand when you're taking the exam. Okay, so let's look at some examples here. A little bit smaller. There we go. Can you still read those in the back? Can you still read it? You can, okay, good. I can't read my own thing here. What's that? Cosine squared, tangent squared. Okay, so the first one I want to do is cosine squared, tangent squared. blue. Okay, so again, what's the strategy here? We're going to simplify this, rearrange it, use identities and algebra to get it some other way that we can either do quickly or we can do undoing the chain rule. So what identity might we apply here, substitute to make life easier here? Anyone see what we might be able to do? Yeah. Okay, so you're looking at tangent. So tangent squared equals what? All right, so she saw that tangent squared x would be sine squared x over cosine squared x. Does it help? Yes. Because cosine squareds go away. So there's a lot of trial and error in this because we could also what? We could say tangent squared is what? Secant squared minus 1. We could say cosine squared is, we could use the half angle. I mean, there's lots of different things we could do here. So it's kind of trial and error, but we see that if we use tangent squared is sine squared divided by cosine squared, something very nice happens. Those go away, right? Those go away. So now the question is sine squared. How are we going to do sine squared? So is that itself, is just sine squared by itself undoing the chain rule? No, because so how could we what would we have? So that this is sine x. What else would you need in this integral for it to be undoing the chain rule? A cosine, right? If you had a cosine x, so if you had sine squared times cosine, then it'd be undoing the chain rule. Do you see that? And your first attempt would be 1/3 sine cubed, right? So if you had a cosine in there, that's one we already know how to do. It was like the last one on your quiz today. Okay? But so it's just sine squared is not undoing the chain rule, so we need an identity here. So we've got some different choices. We could use Pythagorean, and sine squared would be 1 minus cosine squared. Would that help? Kind of takes us in a circle, or now instead of sine squared, we'd have to do cosine squared. Well, that's really the same thing, right? So that doesn't help. What else we got? Half angle. So does that help? 1/2 1 minus cosine 2x. So now that basically we have two different terms now. Can we do antiderivative of 1/2? Or actually the 1/2 just can pull out. So we have the antiderivative of 1 and antiderivative of cosine 2x. Can we do it? Sure, yeah, cosine 2x is really easy. So we got 1/2, antiderivative of 1 is x. And now I've got minus cosine 2x. Antiderivative is? Start with sine of 2x. We'd also need a 1/2. Do we have the right SIGN? Is it to keep it minus there? Is that correct? So derivative of sine is derivative positive cosine, right? So I think we're good on the minus sign, right? The minus is going to say, because derivative of sine is positive cosine, so minus just stays along. So we got it. So since it's generic, plus C. So this is the feel of it. Okay, so here's the thing. That's just a fact that you have to remember because it shows up a lot, is integral of sine squared or integral of cosine squared. This will always be done by half angle formula. So just burn it in your brain right now. Always be on the lookout for just plain old sine squared or just plain old cosine squared isolated by itself. That will always be, you'll always do the half angle formula to get that antiderivative every time. And we like that because so it's like automatic, right? If you get just a sine squared or just a cosine squared, half angle formula. So my experience is, as some of these get a little bit more complicated and we're playing with the identities a lot, that little fact gets forgotten. Don't forget it. Don't forget. Just plain sine squared, just plain cosine squared is easy if you just apply the half angle formula for that, whatever it is. Questions on the first one, first example? Okay, next one here. Why don't you try this one by yourself? Take up 2 minutes to see if you can get this one. I think you should be able to. That's pretty simple. Not too bad. See what you can do on that one.
2x equal to 2 sine x cosine. That's the
Double angle. Use double angle formula. Really, it's all we can do, right? So there's the only thing that's sine 2x here. Okay, good.
And then I combine the cosine to make it cosine squared x. And the 2 can also be on the outside of the interval.
Okay.
And then it's just I'm doing the chain rule.
You see it? So now you got cosine x quantity squared, and you have sine x out here. So that's undoing the chain rule. And somebody else, what is that antiderivative? Did you get it? Yeah, no, you, yeah. Yeah. No, in the red Sun Devil shirt, yeah. Let's see, how do we do? So someone's suggesting a negative. Should it have a negative or not? Derivative of cosine is? Yeah, so when we get to the inside, when we get to the derivative of the inside, we'll have derivative of cosine, which is negative sine, right? And we don't have that negative here. So we do need a negative. Is that what you said at first? Any questions on that one? All right, how about sine cubed? So this one I want you to, again, try it by yourself and then maybe consult. So this, lots of you have the right first step, and that would be to split it apart to sine squared times sine. Lots of you got that. That's key. Now we have a choice, right? So what happens when you apply the half angle formula here? Well, then you get cosine of 2x, when this is sine of just x, and that's a problem. You have two different trig functions with different arguments, different 2x and x, and that usually is a dead end. Okay, usually it is in this case. So taking cosine 2x times sine x. Yeah, so you could apply one of these, but it kind of is a roundabout way of doing what you need to do. So this is kind of a dead end. So what can we do instead with the sine squared? Okay, yeah, so instead of doing half angle and then introducing this different argument, 2x versus we have all just x, you can do sine squared is equal to 1 minus cosine squared. So now the question is this helping? Are we making progress? Yeah.
But now I can recognize that there's a chain rule in there.
Uh-huh.
Because the derivative of cosine is negative sine, so you have some factors to work out. But there is.
Yeah, exactly. So we've got this 1 minus cosine squared times sine. If we want, we could distribute this. Or you actually don't need to, but that's kind of my instinct to distribute the sine. And then we'd have the first term would be sine x. Can we handle that? Definitely. That's easy, right? And then we have cosine squared times sine x. Can we handle that? That's like the last problem we did, right? It's almost the same problem as the last one we did. It's undoing the chain rule. So we kind of found our way out of the tunnel here. Sine x minus cosine squared x times sine x. Okay, finish it. Tell me your name right here in the hooded sweatshirt. Yeah. Did you get it? No? Did you have it just antiderivative of sine? Did you get that? Just the antiderivative of sine? Did you get that much? Negative cosine? Okay, good. Good start. And then, how about this one? Sean in the back, could you do this? You got what? I just didn't hear you. 1/2 cosine squared. So if we take the derivative of that, is that going to give us this thing here? So 2 times 1/2 is cosine to the first times sine. But we have cosine squared times sine. Okay. So third instead. And then am I plus or minus here? Yep, if we think about taking the derivative of this, we get to the derivative of cosine, it's negative sine. So there's our negative there. There's our negative. Okay. So questions about anywhere along the way, about how we made these decisions, why we chose to go the route we did. Anybody have a question? Doesn't make sense. So you want to avoid having products of functions that have different arguments. And what I mean by that is this is cosine of 2x and this is sine of x. That's usually a dead end. That's usually a dead end when you have a product like that. But if you just have cosine of 2x, that's fine. You can handle that, or just sine of other arguments. But when they're multiplied and they have different arguments, that usually means try something else. Yeah.
So I was going to say, it's not quite a dead end, then you can use the half or the double. But what he's saying is it'll usually be much easier instead of going forward with that to back up and try something else that doesn't get the.
Yeah, so there's actually one more down here. You could have, for cosine 2x, you could do 2 cosine squared x minus 1 times sine x. And now you have virtually the same thing we have here, but so it's a roundabout way of doing the same thing, basically, yes. So it's just more work. What's that?
Well, it just kind of makes sense going half and double.
Right, exactly.
Just revert back to the same.
Well, my experience in doing these problems is Really the only thing you use the half angle formula is for just sine squared or just cosine squared. Okay? It doesn't come in much more than that. Okay, let's do one more example. Okay, so something a little bit harder maybe. Secant to the fourth tangent cubed. Okay, so where are we heading here? So let's review our kind of strategy. Our strategy is, can we change the form of this using identities in algebra to set up for something that's doable? Something like, and oftentimes we're kind of setting up for undoing the chain rule. So if we're thinking ahead to staging for undoing the chain rule, what might apply here? What might apply if we're thinking about undoing this? Remember, what is undoing the chain rule? That we're going to have g prime of f times f prime. So what do we got? We got secants and tangents, right? We got secants and tangents, and we kind of want to make something look like this. So what might be an f prime if we have secants and tangents working together here? So maybe let's think about what is the derivative of secant? Secant tangent, okay. And what is the derivative of tangent? Secant squared. Well, let's see. I have a secant to the fourth, so I could pull out a secant squared. And then the question is, could I get the rest of the integral written in terms of tangent? Could I isolate a secant squared as my f prime, and then the whole rest of the integral, could I make it into tangents? Can I do that?
Yeah, there's multiple ways to do it, but it's possible. Because it could be just two secant squares, and then it'll become tangent. You take the integral.
So let's pull out a secant squared here. Now the question is, if I could write everything inside these brackets in terms of tangent, then I'd have undoing the chain rule. Do you see that? If I could get all tangents or forms of tangent in here, then I'd have undoing the chain rule because I'd have powers of tangent and I'd have a secant squared reserved for my f prime. Does it make sense? So can I do that? Can I get all tangents in here? How is that? Is that possible? How? Secant squared is tangent squared plus 1. Now that just, by doing that, now I have two terms, but that's okay. So addition is a piece of cake with antiderivative. We just do them separately, right? So the first term is how many tangents? 5 tangents, right? So it'd be secant squared times tangent to the fifth. And then the other term would be secant squared times tangent cubed. So do you see that we've just found the light at the end of the tunnel here? One of the terms has tangent to the fifth, and that'll be multiplied by secant squared. And the other one is tangent cubed, and that'll be multiplied by secant squared, both of which we can do, because secant squared is derivative of tangent. Can you finish it? See if you can finish it out. Okay, so first term ends up being antiderivative is 1/6 tangent to the 6th plus 1/4 tangent to the 4th. Let's see. So then we come back just briefly here, looking back at the beginning. Could we have isolated a secant tangent? Would that have worked? So if we pulled out a secant tangent, then what would be left? Secant cubed. Well, that's okay, right? Because secant tangent is the derivative of secant, so secant cubed is fine. What else would we have? And tangent squared we could write as secant squared minus 1. So that would have worked too. Do you see that? Secant cubed times tangent, what? Secant squared minus 1. The same thing would have happened. We got all secants in here, and now we've saved its derivative out here. So that would have been an alternate way to do it. Pull out a secant tangent and make everything inside there in terms of secant, which you also do by Pythagorean. Okay, so our